Right. So first, a few non-material things. One is, and I should have said this at the beginning of the lecture of the course, but almost so my lecture notes that I use here, see they're written in my handwriting. These are lecture notes that have kind of existed for several years now, and they've kind of gone around the physics department. Most of the physics 9A instructors use them. And one of the physics 9A instructors decided to throw them all into the book, so that's why they're the same. But I wouldn't want you guys to think that I'm lazy, that I'm just copying from the book, when really the book was copied from what I used to lecture. So, you know, if you think I'm being lazy, I promise I'm not. It's just that the things that I have in my notes that I've been using for years are also now in a book, which is, you know, good for you guys. It means that you have access to my notes. Second thing, midterm results. So it hasn't been completely graded yet. I expected it'll be done being graded by this afternoon. It's like 80% graded or something. 2 questions are still only partially done. But I've looked at preliminary statistics. It looks like that the mean grade, or the average grade was something like the raw percentage, I should say, not grade. The raw percentage, the average raw percentage was something like 135 to 140 points, which is just about a 55%. It's a little bit lower than I was hoping for. I was hoping for a 60, 65%, because that's usually what I get. But don't worry, it will be curved pretty significantly. We're looking at probably an average grade post curve of somewhere between like 77 and 79%, with the standard grading curve. So that would be just under a B minus. So one of the reasons why the average was so low was the first question seemed to trip up a lot of people, which is kind of not a good thing, because that's just a kinematics question. The first question is basically the same question as the archer and the arrow, or the archer and the apple question. So once you do get back your midterms, and they're graded, most of you guys will see that about half of you got it completely wrong, like just didn't have the right setup to begin with, which is, you know, not good. You didn't get 0 points because you did some of it. You got about 30 of 65, but that's what was bringing down the average. So that said, I'm going to probably start introducing more kinematics problems to the homework, so just adding it in a little by little, just so you guys can get more practice come the final, because there will be probably another problem like this on the final, and I don't want you guys bombing that problem. Most of you guys did just fine when it came to the energy question. I mean, relatively speaking, did just fine when it came to the energy question. When it came to the gradient of the potential energy question, it was just that question that really hit everybody hard. So, but don't worry, the average will be pretty standard. Nobody's going to fail this class because of this, unless you scored like a 0 on the exam, then you might, but we'll see. Anyway, so let's get started. So I just want to back up just a little bit, just talk about this principal axis business. So this idea of the principal axes is that the means of rotation, like the rotation vectors, they point in certain directions, right? Right. So like if something is rotating, something is rotating this way, then you could use the right-hand rule and show that that points towards my thumb, right? And you can combine rotations to get a different rotation vector. If something's rotating this way and then also rotating this way, well, you would have one rotation vector that's this way, one rotation vector that's this way. So your rotation vector would point a little bit up and a little bit forward. So it would point up at an angle. And so you could combine those two, and that would just look like a rotation that's going at an angle, not in either of the two planes. But so the important thing is that the important part is not that the axes that you choose, it's not what direction they choose in, because you can always just rotate your coordinate system like we do with free body diagrams, right? Sometimes we have a coordinate system like this, and sometimes we have a coordinate system like this. it doesn't matter which orientation you choose, although there is a particular orientation that's useful. What matters is where those axes are, right? And so the point behind the principal axes is that they describe the axes through which the rotation can occur if there's no external forces. And the reason they do that is because they all intersect at the center of mass. One of the homework problems relates to this, and I want you guys on the homework to think about why it must be the case that if there are no external forces, if an object is rotating, whatever axis it's rotating about has to pass through the center of mass. I want you to think about that, and the easiest way to approach this is just imagine that the axis wasn't passing through the center of mass. Then what would that tell you about the forces? Because you know the net force is 0, so you'll derive some contradiction, and that's kind of the goal there. So let's continue. We have a bit more about axes of rotation. So first, I should mention that rotational inertia is additive. So what that means is if you have two objects both rotating about the same axis, let's say that you have your axis here, and so you have like one object over here that's going around like this, maybe I'll call it 1, and then you have a different object that's not necessarily connected to it, but maybe it's just like connected to the axis in the same way, and maybe this one's rotating here. The moment of you could find the moment of inertia of the whole system about this axis relatively easily, because it turns out that the moment of inertia of a system, and a system is just defined in the same way that we defined system earlier in the course, is just equal to the moment of inertia of the parts. As long as all of those moments of inertia are measured or calculated about the same axis. So in this case, it would work because both object 1 and object 2 are rotating about the same axis. And so you could just add the moment of inertia of each of them. Now, on the other hand, if, for example, let's say I had an object 2 going around some axis here, and then I had an object 1 going around some axis here, well, then you couldn't just add up. You couldn't just add up the moments of inertia about their respective axes, because the moment of inertia for a system is described relative to a single axis, and so which axis would it be relative to in this case? One other thing that I haven't actually mentioned yet, and well, I kind of mentioned it in passing, but I want to make it extra clear, is if you have just a point mass, going around some axis, then the moment of inertia is very easy to calculate. Then the moment of inertia about that axis is just mr squared, where r is the distance from the point mass to the object. Yeah, you could precisely do that. Unfortunately, though, not all of the planets lie in the same plane. So not only it's not that they all go around the same point. Like, for example, if we had a mass going in a circle about this axis, and then we had another mass going like in a different circle about this axis, even though they might be coplanar, the fact that one's tilted means that the axes are different. So you'd have to assume that each planet lies in the same plane as well, and that the axis it goes around is the same. But yeah, you could do that. You could find the total moment of inertia of the entire solar system. And by the way, this business of rotation versus revolution, they're very, very closely related, right? If I have just a point mass going about, rotating about some axis, that's not really a rotation, because it's not like the object is spinning. What's happening is the point mass is revolving around it. But you can compute the moment of inertia associated with that, and it's because it's very much the same thing. In fact, there's a way to relate those two quantities, or those two ideas, revolution and rotation, and this is by using the parallel axis theorem. So by the way, when I write something as a theorem, What that means is it's mathematically true, whereas laws generally aren't mathematically true, they're just empirically derived. So the parallel axis theorem is a thing that you could go and derive in a math class, just from the definitions of things. So what the parallel axis theorem does is it relates moments of inertia, or momenta of inertia, I guess that's the plural, momenta of inertia about an arbitrary axis to the moment of inertia about a parallel principal axis, not momentum. So the important point here is that let me actually just write out the formula and I'll explain in a minute. So the moment of inertia about some arbitrary, that's not how you spell arbitrary, A-R-B-I-T-R, arbitrary axis. The moment of inertia about some arbitrary axis is equal to the moment of inertia about the center of mass axis that's parallel to it. Remember that the principal axes are just axes that pass through the center of mass, plus the mass of the object times the distance between the two axes. So let me give you a picture. So let's say that you have, I'll just draw something lumpy. It's a steak. Steaks are good because they're flat. So let's say that the center of mass is here. And let's say that it's rotating about some axis that passes through it over here. So if you wanted to find the moment of inertia from if you wanted to find the moment of inertia about this arbitrary axis, oh, one sec, I think the cat wants to leave. I locked him in here so he didn't bother anyone. Come on, go on. But then you're not allowed back in. Yeah, well, so the trouble is I have to keep the door closed because my voice is loud and it carries. And so, well, anyway, what was I saying? Right, so let's say that you want to know the moment of inertia about this arbitrary axis. Well, you would find the moment of inertia about a parallel axis that is also a principal axis. So a principal axis is an axis that passes through the moment of inertia, and a parallel axis is an axis that's just, parallel to it. So like another example of a parallel axis would be this one, right? Like the two lines are parallel to each other. So we find one that's both parallel and principal, and that would be, oh, come on, that would be an axis like this. Right? And so if we can find the moment of inertia of this object about this axis, and we know this distance, then all you have to do is add the total mass of the object. I don't know why, add the total mass of the object, multiply it by the distance squared, and then add that to the moment of inertia about this center of mass parallel axis, and you get the moment of inertia of the about the arbitrary axis. Now, how does this relate to revolution versus rotation? Well, let's think about like a sphere, for example, or just a ball. And we're going to take the ball's radius to go to 0 eventually, but if you just have a ball, like a planet, rotating about some axis that it's far away from, that's both revolution, that's revolution, right? But if you want to find the moment of inertia about that axis, well, you would go find the moment of inertia about its central axis. Spheres are generally have their center of mass in the middle of them. And then you would add the mass of the sphere times this distance. Let's say call this distance r. And now let's say that the moment of inertia of this sphere is 0. So if I, cm parallel, is 0, a way that you might get that is if you have a 0 radius sphere, i.e. a point mass, then the moment of inertia about that arbitrary axis, this is using the parallel axis theorem, is just equal to m times r squared. And so this is actually how you can get the moment of inertia of a point mass, or rather, that's where the parallel axis theorem comes from. The parallel axis theorem basically says you can break up the moment of inertia of any object into two parts. You can break it up into the rotation of the object itself. So the object itself is going to rotate on its own axis, and then you could break it up into the rotation of the object, which is this part, plus the revolution of the object, which is that part. And the moment of inertia about some arbitrary axis is a combination of those two factors, because when this sphere goes around, it's going to rotate as it does so, right? Because it'll keep the same, the idea is it would keep the same orientation. So it will have to rotate as well. So that's kind of that's the intuition behind the parallel axis theorem. You take the object's internal moment of inertia, and then you treat it as if it were just a point mass, and then figure out the moment of inertia of just that point mass, and then you just add them together. So this D stands for distance between, yeah, I should make this clear, distance between the arbitrary axis and the parallel axis, and the center of mass. Why was I parallel 0 again? So I'm just saying if I parallel is 0, are D and R in both, yeah, they're the same. I just used D in this case because that's the standard language, and I used R here so you could see how it relates to this up here. But yeah, they're both just distance. So does this mean that you can calculate the rotational inertia of the moon by knowing its distance from the Earth and the rotational inertia of the Earth? No, so Christine, you could find the rotational inertia of the moon about the Earth's axis by knowing its distance from the Earth and the moment of inertia of the moon itself. This is the parallel. This is the parallel axis. This is the arbitrary axis. In this case, this is the arbitrary. And this is the parallel. So the point is the arbitrary axis doesn't have to be like actually arbitrary. It doesn't have to be just any old axis. It might be an axis you're interested in. It's just not the parallel axis, or it's not the principal axis. Generally, the principal axis, the moment of inertia is about the principal axes are known. They're just things that we know already. And then you might have to find the moment of inertia about some other axis, and you can use the parallel axis theorem for that. And I'm actually going to do an example here of where this might be useful. So let's say that we have a uniform rod again. But this time, it's rotating about the center of mass rather than one end. So the picture here is you have your rod, it's uniform, its mass density is uniform, but this time the axis of rotation is there, of length L. So we already know, so we know that this is also where we know that that's where the center of mass is. It's in the middle. So we know that this distance here is L over 2. And we know that it's in the middle because we've calculated where the, so I parallel and I arbitrary doesn't have to be stationary relative to each other. No, they don't. But they do have to be undergoing circular motion, some sort of circular motion. Right, so we know that the moment of inertia about one end of the rod is ml squared over 3. We calculated that yesterday. So we can use the parallel axis theorem. I forgot a word. Parallel axis theorem, PAT, to calculate ICM. So notice if the rotation axis was down here, those two, the axis through the center of mass and the axis at the end are parallel to each other. It's just one of them passes through the center of mass and the other doesn't. So the parallel axis theorem applies. So what we get is that we get the I at the end, which is the arbitrary axis because it's not the one passing through the center of mass, is equal to the moment of inertia through the center of mass plus, well, what's this distance? That distance is L squared, is L over 2. So it's M times L over 2 squared because that's that distance. So we can solve. This is ML squared over 3 minus we don't know what ICM is, so we can rearrange and solve. So ICM is IN minus ML squared over 4. And we know I end is just ml squared over 3, so this is equal to ml squared over 12. And so the moment of inertia through the center of mass of a rod is ml squared over 12. And you could have derived that by doing an integral. And so you would have done something like x squared, but this time you're integrating from negative L over 2, or actually, no, we would use the same coordinate system, 0 to L. And this time, the distance between a point and the axis of rotation, this time it would be something like L over 2 minus x quantity squared. And then you would figure out what dm is. In this case, it's lambda naught dx. And then you could do this integral, and you would get this one. We calculated the moment of inertia about the end last time. Scrolling up, just so I can show you quickly, it was uniform rod right here. But the point is you can use the parallel axis theorem to take moments of inertia that you know and use them to get moments of inertia you don't know. And now that we know the moment of inertia about the center of mass, now we can use that and the parallel axis theorem to get it elsewhere, just by picking a different axis and figuring out the distance between the center of mass and that new point. By the way, just as a note, would the L be to the third? No? Squared? It's definitely squared. Just as a quick note, the center of mass, or the ICM for a rod, is smaller. How did I get L end? What? I end. I just solved for I end directly. Or I solved for ICM. We know that I end is ml squared over 3. I just took this and plugged it in here. No, it's okay. I just don't want to get caught in the weeds. If you do have more questions, so stick around and I can answer them later. Right, so the center of mass moment of inertia for the rod is smaller than the moment of inertia about the end for the rod. And there's an important point here. It's that the center of mass moment of inertia is always the smallest moment of inertia for any system. And the reason for that is that the moment of inertia doesn't just care about how much mass you have, it also cares about how close that mass is to the center, it cares about how close that mass is to the axis of rotation. So the center of mass moment of inertia is calculated through an axis that passes through the center of mass, as is kind of obvious. And so the point here is that the center of mass is the place through which, or for which, all of the mass on the object is closest to it. That's like the most central place to all of the mass. So the contribution that you would get from the fact that that you multiply the mass by the distance squared is smallest. It contributes least. Is I center mass going to be consistent along all the principal axes in that case? So the principal axes for a rod are, I mean, if you treat a rod as a one-dimensional thing, then yes, but rods aren't, like, if it was actually like a cube, it would be different, or not a cube, but prism. So you'd have to, but there are generally 3 principal axes. We're only going to worry about one for now. But yeah, in general, if you rotate the principal axis without changing if you rotate the principal axis, like if you bend it, it's going to change the moment of inertia. That's certainly true. All right, so we're going to sort of change gears here. So the reason why we needed this moment of inertia, by the way, the reason why we took this long detour is because, scrolling up, is because we needed to compute the rotational kinetic energy, right? It shows up there. And so if you want to find the rotational kinetic energy, or in fact, if you want to find the angular momentum or the rotational momentum, you need to know what the moment of inertia is for your object. It'd be like asking, why do we need mass to find the translational kinetic energy? Well, it's an intrinsic part of it. So now we're actually going to get to where it shows up. So let's talk about the dynamics of rolling objects. So on Wednesday, I mentioned that there is a clear analogy between rotational and translational motion, right? But I didn't actually say like why you would use one over the other or when you would use both. I didn't really say that they're related, just that they're analogous to each other. It turns out that they are, in fact, very closely related, especially for a particularly common phenomenon. And this is, let me write down some words. This is rolling without slipping. Translational motion. Become manifestly related. In rolling without slipping. Now, rolling without slipping is a very technical phrase, but you could probably guess what it means just from the definition. This is also often called perfect rolling. So if you see either of those, assume it means the same thing. So rolling without slipping is when you have something that rolls without slipping, right? Kind of obvious. But why is this important? Well, first of all, like the tires on a car, assuming you're not skidding, the tires on a car roll without slipping. Anytime you have something that's rolling as it's falling down something, that's rolling without slipping. And so it does show up a lot in the real world, and this is where you'll start to be able to actually model real life things doing kinematics, doing like Newtonian things. You can actually predict these things accurately. So the question is why is it important for us to study it? I mean, besides the real world phenomenon, it's important because when two objects slip, when two surfaces slip rather, think like a wheel or like a tire slipping on a road, they produce thermal energy, which means that you can't really use mechanical energy conservation anymore. So it makes it harder to deal with. Not that you can't, but it just makes it harder. And the reason why that happens is because when slipping occurs, that means that there is a force, kinetic friction, applied over a distance, the distance over which that slip occurred. And so that means that you would have some some work done by that friction. However, when you're talking about rolling without friction only involves static friction. But not kinetic friction. And we know that static friction generally doesn't do work. And so what that allows us to say then is that the mechanical energy is conserved in a system where we have rolling without friction, and assuming that there's no other external forces, of course. Another reason why this is useful is because it allows us to relate the distance traveled to the total angle rotated. So I'll draw a picture because hopefully this will clear things up. Let's say they have a wheel rolling without slipping. It has some radius r, and let's just look at a single point. So it rolls forward, and so that point is going to move. And if I can get these proportions right, it rolls forward, and maybe by the time that point has gotten here, it will have traveled a distance equal to x equals r theta, where theta is the difference in angle between these 2 points. So you can relate the, I'm saying kinetic friction steals mechanical energy and converts it to thermal energy. But the static friction that happens for an object that rolls without slipping, because there is no kinetic friction, it's static friction, doesn't do work. It doesn't steal energy. The work done by static friction is always zero. So but the other important point I was making here is that you can relate the distance traveled by how many circumferences it traveled along, right? Like if an object rolls once, that means it will have traveled one circumference worth of distance. And so what that says then is that we can relate the speed, the translational velocity, to the rate of change of the arc length of the total amount of circumferences, or the total arc length traveled along your rolling thing. And this is just equal to r omega, because r is constant and the time derivative of theta of displacement is angular displacement is angular velocity. And so the idea here is that there's a relationship between the speed that something rolls and how fast it moves. And that should be fairly obvious. If your tires spin twice as fast, your car moves twice as fast, because each revolution, which covers a set amount of distance, happens in half the time. So you would cover that distance in half the time. So just as a little aside that might be useful for a homework or for a future exam, if this was a spool of rope or a spool of string, v would be the rate that the rope was, the rate that the string was unwinding. So let's say I was pulling 1 meter per second of string off of a large spool. That means that I could figure out, because the string winds around the spool, it means I could figure out the rate of rotation of the spool, assuming I know the radius of the spool. I would just take the speed, 1 meter per second, and divide it by the radius, and that would give me the rate of rotation in radians per second. So we can now so now let's step aside from perfect rolling. We'll get back to it in a minute, but let's step aside from perfect rolling just to talk about total kinetic energy. So let's consider an object that's both rotating and moving translationally. So let's look at the example of maybe 2 rocks connected by a string. And let's imagine that there's no gravity. So draw a quick picture here. So let's say that you have a mass of 2m up here equals, okay. You have a mass of 2m up here, it's connected by another string to a mass of 1m down here. And let's say that, and so you guys could figure out where the center of mass is on this string. It turns out, and I hope you guys can see why, that it would be like precisely here, because this distance should be twice the distance as the upper distance, right? You have twice the mass, so the center of mass should be twice as close to the heavier mass than it is to the lighter mass. If you're not sure, you could do the calculation and figure it out yourself, but trust me when I say it's there. And so let's say that this total length is L, and let's say that this whole system is rotating, right? So just imagine like 2 rocks connected by a string just spinning in space, right? And not only that, the whole thing is moving with some center of mass velocity. So you start them spinning and then you give them a push. So they're just moving while rotating. So the question is what's the total kinetic energy of the system? So we can figure out the total kinetic energy in a relatively brute force way, and that's just calculate the linear velocity, or the translational velocity, of each of the rocks at any given moment in time, and then add them up. So let's just calculate it at this moment in time. So the kinetic energy of the top rock, well, that's 1/2 times 2m times the velocity of the top rock squared, which is 1/2 times 2m times, well, the speed of the top rock, or the velocity of the top rock, is the velocity of the center of mass plus how fast it's moving in addition, because it's also rotating. So that would be the speed, the extra speed that it gets at the top of its arc would be the distance from the top to the center of mass times the rotation, times the angular velocity. Do you guys agree with me here? Does anybody have questions as to how I got this? Yeah, so the idea here is, so this is just the standard kinetic energy for the top rock. But the top rock has two components to its motion. It's both spinning around and it's moving, right? So the question is how fast is it moving? Well, certainly it has, if you doubled this speed, its speed would also increase. But it's also moving because it's spinning, right? So if I look at just an object that's going around in a loop, at the top of its loop, it has some velocity due to spinning. And at the bottom of its loop, it would have a velocity in this direction due to its spinning. And so all I'm doing is I'm adding up the velocity due to its rotation and the velocity due to the center of mass. Yeah, the rocks are rotating about the center of mass. So all I did was just calculate this v spin. And the v spin here for the top rock is just the distance from the top rock to the center of mass times the angular velocity. Right, so we have that. And now we can do some algebra. So this is 1/2 times 2m times vcm squared plus 2r top times omega times vcm, I'm just foiling out, plus r top squared times omega squared. All right, let's do the same thing for the bottom. Now the bottom is going to be basically the same, except the component it gets from the spin is to the left because it's spinning clockwise. So this would be 1/2 times m times v bottom squared, which is 1/2 times m times vcm minus r top, r bottom times omega quantity squared. Then we can FOIL out 1/2 m vcm squared minus 2r bot omega vcm plus r bot squared omega squared. So far so good, I hope. And now we go and we figure out, well, okay, what are these r top and r bottom? Well, this should be L over 3, and this should be 2L over 3, right? Because that's where the center of mass is. So if that's true, then we can find the total kinetic energy as just the sum of these two kinetic energies. So it's 1/2 times 2m times, and I'm gonna do some splitting, by the way. I'm gonna write this term and this term first. So this is vcm squared plus L over 3 squared omega squared. Plus, next I'm gonna write these two terms. This is just so I can, why is the bottom subtracted? Wouldn't the velocity also go toward the positive direction at some point? Yeah, so I'm just calculating it at a single point in time, and I'm acknowledging the fact that the total energy is conserved. So if I calculate it at a single point in time, it should be the same everywhere. If I had done it when this one was at the bottom, if I had done it when the top one was at the bottom, then we would have had a minus sign here and a plus sign down here. But I'm just choosing I'm just making a particular choice. It doesn't matter which one I choose. I could have chosen when they were at some other angle too. It just would have been more complicated. But r bot omega, the reason I stick a negative sign is because the extra velocity it gets from spinning is pointed in the opposite direction of its center of mass. Right, so then we have 1/2 m vcm squared plus vcm, or sorry, not plus vcm, plus 2L over 3 squared omega squared, plus, and now I'm gonna add these two terms here, plus, well, the 2 and the 1/2 cancel, so we have our top is just L over 3, so I'll put 2m. I just want to make this sensible for you guys. So I'll write 1/2 2m L over 3 times omega vcm. That's this middle term here. And then I'm going to have minus this middle term, minus 1/2 m times, I'm missing an extra factor of 2 and a factor of 2 here because there's a 2 in front of both those terms. And then I have 2L over 3 omega vcm. But the point to notice here is that these things cancel out, right? These two terms cancel off because this one had twice the mass, this one had twice the distance. And so what we're left with is this thing that I can write as a different formula. I'm going to combine terms again. 1/2 times 3m times VCm squared. That's just the first term in both of those. It's the first term in both the two terms, plus 1/2, and I'm going to do some simplification here. If you don't trust me, go back and do it yourself. 2 over 3 ml squared omega squared. And so this is our total kinetic energy. Now you might say, okay, well, that's a weird way to break it up, but sure, it's true. What does that have to do with rotation? Well, let's now find the moment of inertia of this setup. So the moment of inertia of the top rock, well, we're going to treat it as a point mass. So and remember, for a point mass circulating about some axis, it's just the mass times the distance squared, L over 2 or L over 3 squared. And similarly for the bottom, it's just the mass times the distance squared. And so the total moment of inertia is just the sum. So it's what? It's 2 times, yeah, it's 2ml squared over 9. 2ml squared over 9 plus 4ml squared over 9, which is 6ml squared over 9, or 2ml squared over 3. So if we look at this formula, this is equal to 1/2 times m total times VCm squared, 3m is the total mass, plus 1/2 times I total times omega squared. So what we were able to do was just by looking at just the translational motion of these two masses, we were able to see that it can be rewritten as just the center of the motion, the translational motion of the center of, oh, I'm lagging a lot, huh? Am I good? Okay, right, so we could have written it as just the translational kinetic energy of the top one plus the translational kinetic energy of the bottom one. That's what we just did. But we could have also written it as just the translational kinetic energy of the center of mass of the the translational kinetic energy of the system. And so to find that, you just find the total mass and you multiply by the center of mass velocity squared, multiply by 1/2. And then you add to it the center of the rotational kinetic energy of the system, which is you take the total moment of inertia and you multiply by the rotational or the angular velocity and multiply by 1/2. And so this gives you a lot easier way to understand the total kinetic energy of a system. And as I mentioned before, it turns out it doesn't actually mention if I had, it doesn't actually matter. No. It doesn't, so is this at a good place? It doesn't actually matter if I had done this when it was in this configuration, or where you have 2m here and m here, or this configuration. Like, it doesn't matter where in the calculation, like where I had done it, because the total kinetic energy is the same regardless. So I just picked an easy configuration, this one, where it's easy to calculate the total translational kinetic energy, but it didn't actually matter. Now, I just want to I don't want to rephrase this. So it is true that you could always find the total kinetic energy of a system like this. However, there's a special case that will simplify this calculation significantly if you're in that special case. So sometimes an object rigidly, I'm going to put rigidly here, rigidly rotates about a fixed point in space. So think, for example, the moon going around the Earth. Assuming the Earth doesn't move. The Earth does move, but we can, or better yet, imagine that like you have you take a ruler like a fixed rod that has very light weight, and then you just put like a big mass here, like a big sphere or something. The point is when I say an object rigidly rotates about a fixed point in space, I mean that the same face that was, or the same, that the orientation of the object tracks with the rotation. So like if this was a square, or let's say that this was a pyramid pointing in this direction, right? That's, how do you draw a pyramid? Something like that. If this is a pyramid, then later on in the rotation, it would still be oriented pointing towards that center point. So that's what I mean when I say rigidly. Like the object rotates with the revolution. So when that's happening, which happens, for example, for the moon, because the moon is tidally locked, then we have that the total kinetic energy is just the rotational energy about that rotational point, which is 1/2 I fixed point omega squared. So the important point is you have to find the moment of inertia about the fixed point through which it's rotating. The reason for that is, it's not very easy to explain in words, so instead I'll explain with math, and then I'll go back and explain in words. So first, let's assume that the fixed point is not at the center of mass. It could have been at the center of mass. Let's just assume it's not, because it's more interesting that way. And let's say that the fixed point is, say, a distance d from the center of mass. Well, then that means that the center of mass follows a circular path of radius d about the fixed point. Then we have our fixed point, and then we have our center of mass over here, so I'll label this fixed point, label this center of mass, and it follows a circular path of distance d. So what does that say about the velocity of the center of mass, the translational velocity? That implies that the translational velocity of the center of mass is just omega times d, right? So that means that the total kinetic energy, which we can always write as the translational plus rotational kinetic energy, this is 1/2 mvcm squared plus 1/2 ICM omega squared, right? It's the moment of inertia of the system. That's when I wrote moment of inertia total here, that was the moment of inertia about the center of mass, by the way. That's important. So maybe I should write ICM here. It is also the total moment of inertia, but it's about a particular axis. Right, so this is the formula that we just derived above, or that we showed at least could plausibly be true. But we know what VCM is. This is omega d squared plus 1/2 ICM omega squared. And so we can simplify. This is 1/2 md squared plus ICM omega squared. But remember from the parallel axis theorem that the moment of inertia about some arbitrary fixed axis that's a distance d from the center of mass is just the center of mass moment of inertia plus md squared. So this is just the moment of inertia about that fixed point from the parallel axis theorem. And so that gives us that this is 1/2 I fixed point omega squared. By the way, I hope that this is obvious, but or actually, you know what? It's not quite that obvious. So I'll go over it. So you may have thought, well, what is this omega? That's the amount of, or that's the speed at which it goes around the fixed point related to the speed at which it rotates, this omega. Well, if you think about it for a second, of course they have to be the same thing, because if the object is rigidly rotating, it makes one full revolution, i.e. one full trip around the object in the amount of time that it takes for the object to rotate one full rotation. So the omegas are the same. But maybe it's not so obvious that that's true. So just think about it this way. The moon takes approximately 28 days to go around the Earth. the moon is tidally locked, which means that the same face always faces the Earth. So how long does it take for the moon to rotate once about its own axis? Well, it also takes approximately 28 days for that same reason, because it tracks the rotation that it goes around the Earth. Right. All right. So we still have quite a bit more. So it is 2. Unfortunately, we do have to keep going, but I will do my best to make it quick. So let's go back to perfect rolling. So for perfect rolling, any potential energy can be distributed into either translational kinetic energy or rotational kinetic energy. And an additional fact, the non-slip condition, the fact that this is perfect rolling, this is rolling without slipping. The non-slip condition, by the way, when I say that, what I mean is that VCM is equal to R omega, determines how much goes where. So let me talk about this for just a second. So when I say any potential energy can be distributed into either translational or rotational kinetic energy, what I mean is, like, imagine a wheel rolling down a hill, right? It initially has some gravitational potential energy, and that gravitational potential energy, as it rolls down the hill, is going to be distributed or transformed into some form of kinetic energy. But whether it's transformed into all translational kinetic energy or all rotational kinetic energy or some combination of the two, that's not necessarily obvious what happens. But that energy does become kinetic energy. So basically, the way to think about this is that whenever you have something that can possibly rotate, like any extended body, potential energy doesn't just become translational kinetic energy or vice versa. It can also become rotational kinetic energy. So the idea here is you just want to think of potential energies and kinetic energies. And kinetic energies now have 2 different parts. There's rotational and translational. But if we're talking about rolling without slipping, which is what we are here, then the fact that the center of mass velocity is directly linked to the angular velocity by this non-slip condition, that tells us, or that will control how much of the kinetic energy goes to rotational versus translational. So a consequence of this is, that's an I, not a T. The bigger ICM is, the larger the fraction of energy is rotational. The larger the fraction of energy kinetic energy rotational gets. So the way to think about this is that imagine that an object didn't have any moment of inertia, i.e. Well, actually, maybe I won't try to justify it just yet. I'll do the math for you and show it to you first. So let's just take a very simple case. We have a standard inclined plane of height h. You have an object of radius r rolling down. It starts off at the top stationary, and then at the bottom it has some speed. Then we can use energy conservation to find various quantities. We have PE initial plus KE initial is equal to PE final plus KE final. And remember, these kinetic and potential energy, or these kinetic energies, are the total kinetic energy, rotational and translational. And so there's no initial kinetic energy, and the initial potential energy is just mgh. And then this is equal to 1/2 mvcm squared. We're going to assume that this bottom is where we're going to call our y equals 0 for the sake of our energy, plus 1/2 ICM omega squared. But so far this says, oh, well, how do you know how much omega, or how much is rotational and how much is translational. But we have an extra equation. We have this relationship that VCM is equal to R omega because it's not slipping. So we can substitute that in, and we get mgh equals 1/2 mv squared plus 1/2 I v over r squared, that I just solved for omega and substituted that in, which is equal to 1/2 m plus I over r squared times v squared. And so what we get is that the velocity, you can do the algebra here, it's 2mg r squared divided by I plus mr squared. And so the takeaway here is and this is ICM, if ICM is big, then the velocity gets, the center of mass velocity gets small, which means that all of that extra energy that would have gone to the translational kinetic energy instead goes to rotational kinetic energy. Similarly, if ICM was very small, then most of the energy will go to the translational kinetic energy, because this denominator will be basically just mr squared. And when that happens, if ICM, say, approaches 0, then we just get our old result for an object sliding down a hill. This is just, well, the m and the r squared cancel, so you just get square root. I'm missing something, actually. I'm missing an h. Gee, I think that it belongs up there. Yeah, it belongs up there. We just get square root 2gh, which is exactly the result that we had when we were talking about an object sliding down a frictionless inclined plane. And just as an aside here, if we're talking about a cylinder or a sphere, in general, anything that has any sort of radius, the center of mass moment of inertia is proportional to both the mass and it's proportional to the radius squared. So you could basically write ICM as equal to alpha times mr squared, where alpha is just some number. For a cylinder, I think it's like, for a hollow cylinder, it's just 1. For a uniform cylinder, it's 1/2. For a sphere, it's 2/5. The point is that it's just some number times mr squared. I'm going to write for circular things. Sometimes. That's only assuming they're uniform, not some things. Sometimes. So at least in the uniform case, there is no dependency on m or r in this calculation, right? Because it'll cancel out, because there's an mr squared there, there's an mr squared here, and then it'll cancel out the mr squared in the numerator. So that's great. This tells us about rolling without slipping. This is how we use it. But there's more applications, because now we can actually start talking about more complicated setups that we've kind of been ignoring in the past. Let's examine massive pulleys. So before, we've had to assume that all of our pulleys are massless, because otherwise things get more complicated. We now have the tools to understand that. So let's just say that we have, instead of a pulley, let's say that we have a spool. A spool is basically a pulley, but it only has stuff coming off of it on one end. So let's say it has radius capital R and mass M, and we just have like a string coming off of our spool. It has mass M attached to it, initial speed of 0. And let's say that it starts off at some height, and then it unwinds a little bit, and it ends at some later height. So that distance we'll call h. So the mass is falling, and it's unwinding this spool. Now, hopefully you can actually see why this is effectively rolling without slipping. And the reason that's the case, if you can't, is that the condition, the non-slip condition that v equals r omega is still met here, because for every 1 meter, sorry, my notes are falling apart, for every 1 meter that this object falls down, it will have to unwind 1 meter's worth of thread or string, right? And so that means, so then you could ask, well, how far does the thing turn when 1 meter of thread has unwound? We're going to put little axis here? Well, you would divide it by the radius, and that would give you an angle. So the non-slip condition here is met. We're just talking about two separate things now. The angle that the non-slip condition refers to, the omega in the non-slip condition, refers to the spool in this case. And VCM refers to the block. But clearly those two things are related. We still have that this is true. That's why I'm talking about this when I was just talking about rolling without slipping. So let's find what the, maybe we want to find out what the speed is of this object when it's falling down, right? Like the speed after it's fallen a distance h. Again, if this was a massless pulley, which means it would have no moment of inertia, then we could just use standard, 1/2 mv squared equals mgh, and then you'd get that v equals square root 2gh. But that doesn't work here because that's not the only source. That's not not only can the mass have some kinetic energy, the pulley, the spool, can also have kinetic energy. So here we have kinetic energy initial plus potential energy initial as usual equals kinetic energy final plus potential energy final. So we have mgh equals, because there's no initial kinetic energy, equals 1/2 mv squared. I'm going to call that just v there because it's not the center of mass of the system. Plus 1/2, and now I need to tell you, let's say I of the spool times v over r squared, because we can use this relationship to solve for omega. Now, as an aside, a uniform cylinder has ICM, a moment of inertia through its axis, equal to 1/2 mr squared. So the picture is that axis rotating that way. So that's a thing that perhaps you could calculate, but most of these things you're not going to be asked to calculate. You'll just you'll either be told it or you can look it up if you need it for a homework assignment or something. There's tables of these things all over the internet, and because once you solve it once, you never need to find it again. All right, so let's substitute in I spool. Ke final equals translational and rotational kinetic energy with P. Yes, precisely. I'll put +0 here. Maybe that'll make things a little bit more clear. I'm just assuming that the potential energy here is 0, and the potential energy, or here is 0, and here is mgh. So let's substitute in. This is 1/2 mv squared plus 1/2 times mr squared v over r squared equals 1/2 m plus 1/2 m v squared equals 1/4 2m plus m v squared. And so that's all equal to mgh. And so now we can solve. So v is equal to square root of 4 mgh over 2m plus capital M. So what does that tell us? Well, if the spool is very, very heavy, if m is much, much larger than m, then v is small. And that kind of makes sense. If the spool has a lot of mass, it'll take a lot of effort to get it spinning. So of course it's not going to fall very quickly because the motion associated with the rotation of the spool stores a lot of energy in it. Similarly, if the spool was very, very small, if it had mass 0, say, then you could just divide and you would get your standard square root 2gh. All right, so another thing to cover, I promised that this is just more examples using this rotational energy bit, or this non-slip bit. So this description up here was about a spool, but it's basically about a pulley, right? Because a pulley is just a spool that has wire coming off on both ends. Would v be constant as the mass falls or no? No. This is just the velocity at a particular height. It's just the velocity after it's fallen a particular height, but it's not constant. It still accelerates, and we'll actually get to how much it accelerates later, but we're not there yet. We'll get to, eventually we'll be able to solve to find the acceleration of the block. Or the downward acceleration. All right, so now let's talk about pulleys with mass. So we were talking about spools, but we have to talk about pulleys. So the question is how does this affect tension transmission? This affect tension transmission. Now the point I'm making here is that we always assumed massless and frictionless pulleys because that allowed us to say that the tension on one end was equal to the tension on the other end. But if we drop the assertion that they're massless, does that change that fact? Well, let's examine it. Let's say that we have the ground. We have a block with sliding with no friction with some initial speed v1 equals 0, connected to a massive pulley to another block of mass m2, speed v2 equals 0. And this is initially, so before, this has omega equals 0. It's not rotating. And let's just say that it has moment of inertia I about its axis of rotation, just whatever it is. I'm gonna see if I can do this efficiently without having to redraw the whole thing. So after, come on, down a little bit. So after, it will have fallen some distance. So maybe this is just, and they'll both be moving at the same speed because they're connected by a rope. But this one will have moved down a little bit. And let's just call that height h. Actually, let's call it x because that's what I'm using in my notes, and I'll probably accidentally use my notes notation. And now this is spinning with some omega, right? The pulley is now rotating. So let's work out let's use the work energy theorem to figure out the work done on the blocks, right? So let's first draw a free body diagram for M1. Well, what forces are on it? Well, the important force is tension. Let's call it T1. There's also normal force up and gravity down, but those don't really affect us at all, so we're going to ignore it. Then we also have our second block, which has another tension force, and we're not going to assume that they're the same anymore, and this has mg downwards. Yeah, we're going to assume no friction. We're still not there yet. We'll get to the point where we can handle friction on everything, like on the pulley and on everything, and it'll be glorious once we do. But let's just assume a massive pulley that's frictionless. So we're going to imagine that the rope and the pulley are not part of the system. So we're going to compute the work done on the blocks. So work done on block 1 is equal to, well, the work energy theorem is that it's equal to the change in kinetic energy, right? And so what does that imply? Well, the work done on block 1 is equal to, well, it'd be T1 in the I hat direction dotted into dx I hat over whatever distance it travels. It travels a distance x. Maybe it starts at position 0, goes to position x. And so this is just equal to T1 times x. Similarly, we could figure out so what this tells us, by the way, is this tells us that T1x is equal to 1/2 m1 v squared. All right, let's do the work on the second block. This is still WKE2. And so the work done on the second block, well, this is, well, the force we have, let's say downwards is positive, just for the sake of argument, just to make things easy. So we have mg going down, m2g going downwards, and then we have T2 going upwards. I hat dotted into d, let's call it dy, or no, let's call it x again, dx I hat. And then we go from 0 to x because it falls a distance x. And so this is just equal to m2g minus T2 times x. So that tells us that m2g minus T2 is equal to times x. is equal to 1/2 m2 v squared. All right, so we have two equations so far that are going to be useful. Oh, wait, this one and this one. So now we want to compare T1 and T2. So to do that, we'll just subtract them. That's how you compare things. So T1 minus T2 is equal to 1 divided by x. So I'm just moving the x over onto the other side. It's 1 divided by x times 1/2 m1 v squared minus mgx plus 1/2 m2 v squared. Hopefully you guys can follow what I'm doing here. And so we could actually rewrite this as 1 over x times the change in kinetic energy of the blocks plus the change in potential energy of the blocks. So this term is the change in potential energy. The potential energy decreases because the object falls. These two terms are the changes in kinetic energy. The kinetic energy is increasing, so because they're speeding up. So but delta KE blocks plus delta PE is equal to delta ME. That's the change in mechanical energy of the system. And so we can then ask, so that means that sorry, let me rephrase. The point I'm trying to make is that this is almost the total mechanical energy of the system. This is not quite the total mechanical energy of the whole system. Because we've neglected to include the mechanical energy of the spinning pulley. So if this was the total mechanical energy, well, there's no external forces, so sorry. Yeah, so then this would be 0. I.e., if the total mechanical energy is conserved, then it would be 0, and that would mean that the tensions are the same. But the total change in mechanical energy is equal to the total change in potential energy plus the change in kinetic energy of the blocks. We're almost done. Plus the change in kinetic energy of the pulley. And this, it goes from 0 kinetic energy to some kinetic energy. So this is equal to 1/2 I omega squared, and that's not equal to 0. As long as the mass is not equal to 0. Because if the mass is 0, then the moment of inertia is 0. So T1 minus T2 is equal to 1 over x times the change in mechanical energy minus the change in kinetic energy of the pulley. And this thing is 0, just by energy conservation. The total mechanical energy of the system, because the pulley is part of the system, there's no external forces, yada, yada, yada. And this is the kinetic energy of the final kinetic energy of the pulley, which is not 0, minus 0, which is the initial kinetic energy of the pulley. And so what that tells us, because this change in kinetic energy is positive, change in kinetic energy of the pulley, it tells us that this is positive because it goes from 0 kinetic energy to positive kinetic energy. So the change is positive, which then tells us that T1 minus T2 is negative because we have a minus sign here. Or that T1 is less than T2. So all of this takeaway was to say that indeed, once you worry about the pulley having mass, the tensions aren't the same anymore. They're actually quite different. And you could figure out how much they differ by figuring out this x and by figuring out this change in kinetic energy for the pulley and so on. But the point is you can no longer treat them as the same. One way to see this is that in order to get the pulley to rotate, there has to be some sort of net pull or like net force pushing on it. And so if they were equal, because they're pointing in opposite directions, if we look at I just divided through, there's an x here and there's an x here and an x here, and I just divided through the x. So let's now look at the Pulleys diagram. So the pulley has a force pulling it this way, that's tension 1, and a force pulling it this way, that's tension 2. And that's just from Newton's second law. So how would we compute a similar result for, say, 2 ropes attached to M1 and 1 rope attached to M2? Are the ropes connected to each other? Like, I don't understand how you could have different number of ropes on either end of a pulley. Actually, I'll answer that in just a second. I just want to finish going over this. So if we look at the diagram of where the forces are applied on the pulley, we see that T1 goes to the left and T2 goes down. But the whole thing has to rotate clockwise, which means that T2 has to be greater than T1, because otherwise the forces on either end, if they were equal, there would be no force to get it rotating. And actually, that brings us to another point, which we'll talk about next time. It gets us to torque. So in this example, we only computed the work done on the blocks, but we didn't compute the work done by the pulley. Sorry, the work done on the pulley. And so in order to do that, we actually need to incorporate force into rotational motion. We need some sort of rotational equivalent of force to talk about how you can do work that results in rotational motion rather than translational motion. And that gets us to this idea of torque, which we're going to talk about next time. All right, so I'm going to stop recording. I'm going to answer some questions, and then I got to run.